Okay, greetings everybody. My name is Bill Renaud. I'm with the Oak Ridge Leadership Computing Facility, and we'll be talking today and in another session about some Linux basics with somewhat of an angle towards HPC, but Linux basics in general should help you even if you're not an HPC user. There will be a couple of parts to the presentation today covering mostly general concepts and terminology, a little bit about shells and starting to work with files and directories on the system. The other part will focus on some slightly more advanced tasks of a little more file and directory manipulation, process management, file permissions, and some of the other day-to-day operations that you might see when you're using a system. Giving credit where credit is due, did find some good information for this presentation with the links we have listed here. One Unix intro site from the UK. That's actually a pretty good site, very in-depth, that steps you through quite a few different lessons, so you might want to take a look at that. Found some info in one of the previous seminar series lectures, and also the GNU.org page. Some good information on different utilities there. So moving into part one, I know some of the other sessions have discussed logging into a system, so this assumes that you have some familiarity with that. If not, there's plenty of tutorials that you can access online on your simple secure shell operation to connect to the system. You'll also notice I use some different fonts in the slides. Many of them in that monospaced font I will use for a lot of commands, just to help set them aside a little bit. And I'll be giving a brief discussion of the commands. Most of them get very, very in-depth. So they're kind of your license to learn. You know the command, so you know your starting point to get some additional information. Looking at Linux or Unix in the HPC world versus the normal world, for an end user, it's essentially the same. There's not much difference. The basic operating system is the same regardless of what environment you might be using. When you're working in an HPC world, you will have larger, sometimes much larger file systems and storage capabilities. You'll be dealing with what's called batch queuing systems and several other features like that. And in the HPC world, as compared to a desktop Linux installation, you will seldom actually be at the system's main terminal. You will be connecting to it remotely. On a desktop installation, if you're using it for your laptop or a home computer or something like that, you very well might be using the main terminal for the system. So again, you'll use some utility like Secure Shell SSH to connect to the system. You may need to do some work with the graphical environment. That's called X11. We'll talk about that later. That's in part 2 of the slides, some tips for working with that. Moving through some general concepts, everybody talks about Linux as an operating system. Technically, that's only referring to the central part of the OS that is managing the system and doing the actual interaction with the hardware for you. There is much more to an operating system, many more utilities. So Linux is combined with software from the GNU project to make a fully capable operating system. Most of the commands that we use are from that project. So you will occasionally see this GNU/Linux or GNU plus Linux, some styling like that, which is a more technically accurate name. Although in general, it's kind of become a genericized term that everybody refers to the whole thing as Linux. The other way does give a little bit of credit where credit is due. You'll also hear of a distribution or a distro. That is simply a bundling of the Linux kernel, OS software, and other software to get what you use on your system to make it a fully functional computer for you. This is what most people mean when they call Linux an operating system. There are several popular ones that I have listed, Ubuntu, Red Hat, Debian, SUSE. There are many, many more. There are several websites like distrowatch.com and some others that give lists of different ones. Linux systems are very common, as you may or may not know. They go from everything to very small embedded control devices. I know somebody that uses a very small Linux system to control the fan on a smoker for smoking whatever they might be cooking. It's on smartphones. Android is a Linux-based OS, laptops and desktops, servers all the way up to the most powerful supercomputers in the world. Most Linux systems, most distributions provide both command line and graphical interfaces. We will focus mostly on the command line. If you know that, the graphical interfaces are intuitive since they're implementing the same things. We have two things to keep in mind in talking with the system, or two large concepts of users and groups. Again, a user is you. It's the individual that has access to the system. It can also be an account that is simply set up to manage some task that doesn't really tie into a person. That's more of an administrative discussion than an introductory discussion, though. And then we have groups, which are collections of users. They may be based on the research area you're working in. It might be where you're physically located, your organization structure, or something else. But a group is simply a collection of users. The system understands users and groups by particular numbers. Those are called the UID, the user ID, and the GID, the group ID. We're human beings. We don't normally deal with large groups of numbers very easily. So the system maps those over to names and to text strings for us to deal with. For example, I might be user Renaud B and have the user ID 501. The system knows me as 501, but when I log in and when I look at things, it talks to me like I am Renaud B, because that's easier for human beings to deal with. The system really does that for most things. At the lower level, it's managing things as numbers and converting that into a format that is a little bit easier for people to deal with when we have to interact. A great example is web addressing. Computers on the internet are known by a number, their IP address, but we don't connect to that. When we're going to CNN.com or something like that, we use the text string to connect. Same principle there. The shell, this is a very basic program through which we interact with the system. There are several available. Bash, the KSH, which is Corn Shell, C Shell, Turbo C Shell, and some others. These are largely a factor of user preference. Whichever one you get comfortable in using is typically the one you stick with. A side note, if you're not aware, users tend to be very passionate about their shell of choice to the extent that theirs is right and everything else is wrong. That's just, I guess, the way we are sometimes as users of the system. Different shells basically provide similar features. They just do them in slightly different ways. So it's a matter of what syntax you get used to when you're using the machine. There's also a concept of a shell script, which is essentially a very small file containing several different commands. It's to automate things that you might be doing on the machine. And they're essentially very basic programs. So as we talk a little bit more as we go on in this lecture and the next one about different commands, you will get the feel for how you might put these together in a very simple program in a shell script. Commands, just mentioned those. These are the basic programs through which we interact with the system. They're typically very short, maybe just 1 or 2 letters. One of the things you'll notice with Linux and Unix, which is a related operating system, the commands are very short. Many of the things we do are only 1 or 2 letters to make it faster, to make it less for us to type, so that the lazy programmers and all of us are happy. The commands are very flexible. They take, most of them take many options. Some of them can take tens, or there's probably some out there that take hundreds of options. These are normally letters or a couple of letters put together. You'll notice them because they typically have a dash in front of them. Again, you'll see a little bit more of this as we move along. And they're typically single purpose. That is something that you'll notice. The commands do one thing and they do it very well. We might want to do a very complex operation. There's not necessarily a command for that. What we have to do is take several of the commands that we have, put them together, and build the more complex command that we need. If you're familiar with computer architecture with CISC versus RISC architectures, it's kind of a philosophy similar to RISC of reducing the instruction set down, and if you need to do something more complex, it's on you to put that together. And in general, we'll see a form of commands as the command name, then some 0 or more options, and then the different arguments for that command. We've talked about several of these concepts with the user, the shell, the kernel, and the actual underlying hardware. That's kind of a visualization of how they are layered on top of each other. The user is really interacting with the shell interacts with the kernel, and that's what interacts with the hardware. So that's how everything works together. A final word on general concepts is getting help. One of the best ways to get help when you start using the system is ask someone that's familiar with it. That's always one of the best ways to get help. There's always asking the web, ask Google or whatever your favorite search engine might be. Once you get a little bit more comfortable with the system, a little confidence in what you're doing, and when you know the command that you're trying to run but might need a little help with running it, you can use help options to those commands. Most of them take some form of help option. The system has built-in manual pages. It's actually a command, the man command, so there's an example for a command called pwd. You could do man pwd and that would give you information. And then, especially on Linux systems, it's composed to other versions or derivatives of Unix. There is the system info command, which is similar to man pages. Info pages tend to be more in depth, and it's a little bit more interactive for you than just a lot of data scrolling past. If you've ever heard of a philosophy called least user privilege, Linux uses that. This essentially, the philosophy is to let the user do their job, but don't give them access to do more than what they need. Don't let them do things that could compromise the system. If you run Mac operating system or Windows Vista and 7 and later versions, they do the same things. When it's prompting you for a password to do some administrative operation, you're actually authenticating as an administrative user to be able to do that. As your normal user, you can't. Linux operates the same way. It's to protect the system. Everything on the system is associated with the user, like I mentioned on the second or third slide. A lot of those users are actual real people like you and me, but some of them are system accounts. There's also a special user account that I'll mention once or twice as we go on called root. That is the system administrator. We talked about the numeric user IDs. Its user ID is 0, so right there where we start counting computer-wise with 0 is the administrative user. Some other things that are important to keep in mind. Linux assumes you meant to type whatever you typed. There are commands that you can run that can be very destructive, that can wipe out all of your files and do things like that. And Linux will happily do them when you type the command. It doesn't, unless you specify certain options, it's not going to ask, do you really want to do this? It will gladly delete all of your files for you. We'll talk about what's called recursive options, using wildcards. Exercise caution when you're using those. Now, you typically will not be doing things as root in an HPC environment because there will be other administrators for the system. But if you're using it in some other environment on a desktop, when you're doing operations there, think before you press enter. Make sure you've typed exactly what you meant to type. You certainly do not want to use the root account for day-to-day operations. You only use it when you absolutely have to. We will joke around. Sometimes you type a command and you wonder why that command is taking as long as it's taking, because you don't expect it to take a long time. You expect it to operate very quickly. When that command runs for a while, you wonder what you accidentally told it to do that was much larger than what you meant to. So you want to avoid the why is that taking so long feeling that we can sometimes have. A little more on normal computing versus HPC. HPC is a client-server arrangement. Again, you're using your laptop, desktop, or some other system to connect in. I mentioned Secure Shell earlier. There are some other connection utilities. Telnet or Login are some older ones, but some systems do still use those. Whichever you might be using, you need to have the appropriate client software on your system. Most Unix-like systems, and when I say that, I'm including Linux. I'm also including Mac OS because it is a Unix-based system, will have Secure Shell. Though they may also have those other utilities as well, but Secure Shell has become somewhat ubiquitous in for connecting to lots of different systems. If you're using Windows, there's a utility, there's quite a few utilities. One that I'm very familiar with and like using and suggesting to people is called Putty, P-U-T-T-Y. You can search for that and find it fairly quickly via Google. It's free. It provides all of these different protocols, including SSH. So it's a pretty good one if you're operating on that type of system. Moving on into actually working in our different shells. Again, these are the ways through which we interact with the system. You can think of them as the command prompt and what is asking you what command you would like to run and then handling running it for you. But they also provide some programmatic control structures like if, then, else statements, while loops, and other similar structures that allow you some degree of programming. The syntax for those is one of those things that differs from shell to shell. So it's a case of figuring out which one you're more comfortable with, and once you start using that, you can learn the particular syntax for that shell. Most of them, most modern shells do have some form of tab completion, and what that simply means is you type part of a command or part of a file name and hit the tab key, and if whatever you're typing the system can uniquely match, it will fill in the blanks and complete the command for you. You see my lazy programmer note down there. That can save you lots of keystrokes. And if you have special characters in file names like spaces and things like that, that historically were not parts of file names, but although they're certainly legal, you have to handle those specially. There are certain control characters that we'll talk about a little bit later that you have to put in to make the system recognize that when that space is in there, it's part of the file name. You're not giving it two different file names. When you use tab completion, the system fills in the blanks and it does all of that for you. So it can save a considerable amount of time. All users on the system will have what's called a default shell. That is, when you log into the system, that is the program, the shell program that is started to handle your use of the system. You can start another shell, that's certainly legal, or you can have the administrators change your default shell if you want to use something else. But once you log in, your shell is started, and then you're given a command prompt. How this appears will differ from system to system. For simplicity in the slides, when I give a command example, I just have a simple $sign. You can customize it to whatever you like. You can see the one that I have down there, and actually when I copied it over, it truncated a little bit of it. I'll have my username and the host name listed there, so when I just look at the screen, since I'm often connected to many different systems, I know which system that is. I also have the directory listed to the right of the host name, so I know exactly where I am on the system. And then I put the $sign on the next line just so that I have my whole screen to type the command. That's simply a personal preference. Some of the other features that the shells provide are variables. These can be very useful in different commands and scripts, different programming languages, Perl, Python, even even your compiled languages like C can read environment variables and act based on those so they can be used to pass information back and forth. Again, this is another thing where different shells use different syntax to set these variables. There's two types of variables we need to be aware of. They're called shell variables and environment variables. A shell variable only exists in your local shell. If you start a shell script, which getting a little bit more technical, actually when the shell script starts running, it starts another shell. That's called a subshell. And shell variables will not propagate from one to the other. Environment variables will. So they exist in your local shell and in any subshells that you create. When you're setting them on bash for shell variables, you simply say the name equals the value. For C shell and TC shell, you use the set command. So set variable name, and there's no equal sign, then you just give it the value. For environment variables, it's a slightly different command. For bash or corn shell and similar shells to that, you simply add the word export before the variable name. So in my example there, export myvar equals some value. For C shell, you set them exactly how you set shell variables, except instead of using the word set, you use the word set env, so set environment. So that part can be a little bit easier to remember. You'll see in the examples that I have, and in a few of them listed on this page, that the shell and environment variables that I listed are capital letters. That's not a requirement, but it's certainly the common practice that you'll see on the system. Just helps them stand out a little bit more. Some handy environment variables that you will have access to on the system, one of them is called path. The path variable simply has a list of directories separated by colons that tell the system where to look when you type a command. So when you just type 3 letters, one of them that I gave you a few slides ago was PWD, the system needs to know where to find that program. So the way it finds it is by searching through all of the directories in your path. Oftentimes you'll need to update this if you add a program or something else that you want to be able to call by its very short name. You'll need to add to your path. When you do this, you want to be careful that you don't wipe out everything that's already set in your path. So if you look in the example, I have export. Again, it's an environment variable, so we use export. Path equals /sum/new/directory, and then a colon, and then a $sign and the word path. So what that means is set path equal to this new value followed by everything that's already in path. So I'm prepending some new directory to path. The second point that I make, if you need to use some command or run a program that you compiled that's not in your path, you have to tell the system where to find it. So updating your path to include the directory in which that command is located is one way. The other way is using what we call a fully qualified path or an absolute path. And you start at the very beginning of what's called the file system. We'll talk about that in a minute. And tell the system exactly what path to take to find your command. So I have the example there of looking through a few different directories. Another helpful environment variable, $user, that's your username. Now you may wonder, why do I need the system to tell me what my username is? I used it to log in. Well, a good example is it's helpful in scripts, especially if you're working in a research group where everybody might use the same script and you need to reference some specific file that each different user has in their home directory. You can use this $user flag to fill in the blank in a path to make you able to write one file that everybody can use, or one script that everybody can use. Also $home, that is your home directory. That is your particular place to store your files. Talk a little bit more on that later, but sometimes you do want to reference that, so it's easy to do with that variable. Shells often when we're using the systems in general, we deal with strings. So the system by default is going to see the space as meaning the end of something and the beginning of something else. If we're using a string, like several words put together or something else that has spaces in it, but it's all supposed to be one item put together, we can use quotes to tell the system, no, the space does not mean it's another item, this is all together. And there's several different types of quoting that we can do. The single quote, otherwise known as apostrophe, identifies what we call a literal string. So that means if we have some special characters that we'll talk about in there, the special characters don't have special meaning. The $ is actually a $. It doesn't have the special meaning that it normally has. Double quotes. These also identify a string, but it tells the system those things like the $ do have special meaning. So I have examples of this that'll make it a little bit more clear. The backslash is another way to remove the special meaning of the next character. Usually use that in double quoted strings. The good example that I've been mentioning here is the $ that does have some kind of special meaning. We may actually want a $ in our string. So if we just put the $ in there, the shell will assume we mean something special by it, but if we put that backslash in front of it, it tells it to remove that special meaning and we actually mean the character itself. There are also back quotes. Normally this is on the same key on your keyboard as a tilde. It's kind of a backwards facing apostrophe. These are used to capture the output of a command. You can see my note. In Bash, using them is kind of deprecated. They're trying to move away from that in favor of surrounding the command in a $ and then parentheses. But in that green box, both of those would do the same thing. So we've talked about commands. We'll start with a few of them that we'll use in a couple of examples and that also are very helpful in using the system. Echo. Echo simply prints something to the screen. Hostname displays the system's hostname. If you're the administrator, it will also permit you to set the hostname. If you're not the administrator, obviously you cannot go around changing critical settings like that. There's a command called whoami that will actually display your username. The sleep command basically tells the system to do nothing. You give it a number, so if you say something like sleep 5, you tell the system don't do anything, pause here for 5 seconds. A lot of times you'll use that in a script when you know you need to wait for something else to happen, so it can help you do some type of synchronization. The colon is a command. It's essentially a command that says do nothing. This is often used in scripting when you need to, if you're doing an if then else type structure and for some reason you need to, the way you write your logic dictates that one of those branches doesn't need to do anything, you just use the colon as a no operator. The semicolon, not specifically a command, but it's a command separator. What this allows you to do is type multiple commands at one prompt and only have to press enter once. You may wonder why you want to do that, but I'll use it in a few examples in these slides, and just trust me, it is useful when you're using the system. Also, another special character, not specifically a command, is the £, the number sign, which begins a comment. It's useful in scripting. When you create a shell script, which I mentioned earlier, any text that the computer sees in there, it's going to assume as a command that it needs to operate. Sometimes you need to put some notes in there for you or for somebody else that might be looking at that script later on. The £, begins a comment that tells the system, this is text for human beings, you don't need to worry about it, move on. So it'll go on and ignore it. So here are some examples combining some of those basic commands and some of the quoting. So in the first example, I set the environment variable my host to the host name. Then I echo it. I've told it to just print $myhost to the screen, and that setting was set in this example to Titan. In the next two examples, I essentially set the same string, but once with single quotes and once with double quotes. So when I echo those two variables, you can see the difference there. The myvar3 is an example of double quotes with a backslash. So you see the example of the effect that that has on something. I mentioned wildcards. A lot of times when we're doing something, we may be dealing with files, or we may need to match a lot of strings for some command that we're typing. It can be really tedious and really error prone to type file after file after file. If you want to perform a particular operation on 100 different files, you don't want to type a file name 100 times. So we have wildcards that help us with this. There are a couple there. The question mark matches 0 or 1 characters. So if you have 10 files and they're named file 0 through file 10, you could use file question mark to match all of those. Again, I have some examples coming up. The asterisk matches 0 or more characters. You can think of that as infinite question marks. Sometimes you will see brackets, square brackets used in a command. This is used when you want to match one letter, any one letter in those brackets. Wildcards are part of a larger topic called regular expressions. We won't really go into depth on that because that could, I say in the slides, it could be a week-long class, it could be a semester-long class. That is an enormous topic. One of the good guidebooks on that, I think, is well over, it's either about 800 or 1,000 pages. So that is certainly a very in-depth topic. So let's assume we have a lot of files. I've got 9 of them listed there, file 1, 2, and 3, and they may or may not have an A or B after their names, .dat. So some of the wildcards that we might use, fi asterisk, or sometimes you'll hear people say star.dat, would match all of those because that asterisk can match 0 or more characters. File question mark.dat will only match file 1, file 2, and file 3 because it matches 0 or 1 characters. To match file 1a.dat, it would have to match 2 characters, so it doesn't match that. The third example shows you the use of brackets to only match file 2a and 3a. And then what might be a little bit surprising, the bottom one, file with 2 question marks .dat, actually matches all 9 strings. The important thing to remember there is the question mark can match 0 or 1 characters. So every one of those file names is the word file followed by 0 or 1, or followed by 1 or 2 characters, and we have 2 question marks, and then followed by .dat. So since that each of those question marks can match either 0 or 1, it actually matches all 9 of those strings. There's a topic of redirecting output. Sometimes you might want to run a command and capture that output. Maybe it's because the command generates 5,000 lines of output, and when it flies by you in 2 seconds, you can't read all of it. Or maybe it's because you want to use that as input for another script, or somebody at tech support asked you to do it so that you could send them the output that you're receiving. There is slightly different syntax between different shells, as with many other things. And when we're talking about output, we call them streams. Those are basically the different kinds of output we might be dealing with. The 2 we consider are standard output, which is what a command is normally going to put out as when you type it. And then there's standard error, which is normally what happens when it encounters some type of error message. Those actually are separate. They're not all printed to the same place. So when you're redirecting output with bash or similar shells, you may or may not want to overwrite the file that you're creating or that you're putting the output into. So you see the first and second examples are putting the standard output into a file and overwriting it if it already exists. The second example simply adds to the bottom of it. Then we can see using standard error, or in the bottom 2 examples, redirecting standard output and standard error. In the bottom example, that syntax is a little confusing where the line ends with 2 greater than and 1. If you're familiar with C programming, you're familiar with pointers and references. You can think of that as a reference. You're saying 2, which is means the standard error string. The system considers standard output to be 1 and the standard error to be 2. So you say 2 into the address of 1. So 2 goes to wherever 1 is, and that's kind of the way I remember that syntax. Oh, with C Shell, there are more options. It also gets very, very confusing if you're trying to redirect standard output and standard error into different places. That's the second from the bottom line. You have to use some very creative control structures because it really doesn't do that by default. This is one of the things that a lot of people don't like about C Shell. So again, that's one of those personal preference things. And you also see in some of those examples, I use this weird file named /dev/null. That's an actual file that exists on the file system. And anytime you redirect any output into that, the output simply goes away. So if you don't care about your output, you just need to throw it away somewhere. Sometimes we'll call it the bit bucket. That's where dev null comes into play. You can also redirect input, maybe a list of data for your script to process. This involves another stream called standard input, standard in, or stdin. Normal redirection you just do with a less than file. The command example that I have there says, take all of the data from myfile.in and send it to the script named run.sh. So every line is sent to that script. There's also what's called a here document. You may want to create your file in place instead of using one that already exists. We do that with the double less than sign. And you can see right after that double less than sign, I typed a string. I always type EOF into file. That's just a personal preference. It can be anything. Then I type all of the data that I want it to contain. And then on a line all by itself, I type the same thing that I typed after the double less than sign. That tells the system, I'm done, you can begin processing now. So that's just the end delimiter. That delimiter will not appear in the file that is sent to, in this example, run.sh. So my script will only get line 1 and line 2. Moving on a little with files and directories. We talk about what's called a file system on Linux, both standard and HPC installations. It is a hierarchical file system, so basically everything starts, you can think of it as a tree or looking like an organization chart or something like that. Everything starts at the top and branches out underneath that. So the top is simply called / or it's sometimes called the root directory. Again, a good reference is if you're thinking of a tree, the trunk where it meets the ground, that's the root, and that's where everything starts from. Some common directories that we might see, etc, also called etc, has a lot of configuration files. There might be a directory called home, which contains user home directories, directories for commands, temporary files, libraries that the programs we create might need to use, and directories for log files, and there's quite a few others. These can differ greatly from system to system. Now, Linux can use multiple hard drives or DVDs, CDs, flash drives, anything you can think of, but it still arranges all of it in this unified structure under /. So if you install a DVD, it's probably going to be in something like /media/DVD or something similar. If you're dealing with a GUI interface, that makes it really easy to find. Otherwise, you might have to search a little bit if you're using the command line. On the other hand, if you're familiar with Windows, it places each device as the root of its own file system. So you have your C drive, D drive, etc. So that's kind of a comparison between the way the two of them operate. So again, looking at the very simple file system, if we do an ls, which is an operation to list files, we see everything listed under that file system. When we're working with files and directories, I mentioned earlier we have two different ways to refer to a file, what's called a relative path and what's called an absolute path. The absolute path, as the name somewhat implies, tells you exactly where to find something. So you don't need to know anything about where you're currently located. This gives you the roadmap directly from the beginning of the file system all the way to the file. And you see the example there. The relative path tells the system the location of the file in terms of our working directory, or maybe in terms of something else. So for that file above, home, some user, my directory 1 / the file, assume we're already in /home/some user. The relative path to that file would simply be mydir / the file. The system, since you did not begin that with a slash, it assumes you want to begin with where you're currently operating. So working with some files and directories, we already listed a couple of these, but some of the common commands that you might use. pwd prints what's called your working directory. That's the directory you're currently located in. cd changes to another directory. mv moves a file. That includes renaming a file from something to something else, even if it's staying in the same directory, is still considered moving the file. ls that we just saw lists directory contents. You can make a directory with mkdir. I tried to do a little research, couldn't figure out why they didn't originally go with just md, but they didn't, so that one's kind of an outlier. If you want to delete a file, we actually call that removing, so that's rm. Important to keep in mind that when you remove the file, it's gone. There's not a recycle bin like on some of the other OSs we might be used to. Again, that goes back to Linux assuming you meant to type that. If you said to remove it, you didn't want it, so it will get rid of it forever. rmdir, remove directory. So remove is a kind of a particular command. Normally it will not delete a directory, it only deletes regular files. So this other command, remove directory, exists if you want to delete a directory. ln creates what's called a link. We'll cover that in the next session. File can tell you what type of file something is. That can be important with some of the commands like less, more, and cat that will display a text file. You want to make sure that the file is in fact a text file, and the file command will tell you that. If you try to display a program like it's a text file, you get lots of strange characters. If it's your desktop system, it will beep and make strange noises. So that's why we have the file command. Strings can show you printable strings in a command or a binary. That actually can provide very useful to see maybe if a directory or something is hard-coded into the file. Strings can show you things like that. The head and tail command show you respectively the first few lines and the last few lines of a file. That can be useful as well. Again, some more examples of using some of those commands, printing the directory, changing, moving files around. So you can see examples of those commands. More commands with files and directories. Quota shows you your file system quota, essentially how much storage you're permitted to use in the file system. df shows how much free space the disk has. You can think of it as disk free. du shows the disk usage of a particular file or directory. So we have an example there of the quota command for a user named SomeUser, and then it can be a little bit difficult to read all of the numbers, especially in this example because the numbers are very, very large. But essentially the first number that shows up means that user is using about 16 gigabytes of data. They have a quota of about 52 gigabytes of data. Actually, their quota is 50. That's just the way the system rounds that up. And then some examples of using the df command and the disk usage command. If you look at the bottom of that disk usage command, the options I gave it told me to summarize the usage in kilobytes. And strangely enough, that's showing about 16 gigabytes of data. So that might very well be the same directory that we just reported the quota for. In the example above for the disk free command, you can see the usage. The header for that second column is 1K blocks. So it's telling you kilobytes basically. How many blocks are available on the system, how many are used, how many is available. And since a lot of times we're very bad at doing math just by looking at very big numbers, it tells us the percent use. So all of those file systems, except the second and except the bottom two, are fairly empty. The top one is only 23% used, and all the others are under that until you get to the last two. A little more info on the ls command. This one literally takes tons of options. Some of the important ones, lowercase l shows you a detailed listing of the file. So instead of just the file names, it gives you more information like the date that it was modified, how large it is, and some other information that we'll use in some later commands. The A option says show all files, even hidden files. The system is able to hide certain files so that you don't normally see them, so they don't clutter up your screen really. A lot of times the hidden files are configuration files for different programs that you might use. So normally you don't want to see those, so they're hidden from you. The capital R tells it to operate recursively. That simply means I don't want to see just this directory. I want to see this directory and all of the subdirectories under it and all of the subdirectories under those and so on. So it shows all of the contents of those directories. The remove command does take some useful options. It also takes some that are really dangerous or can be dangerous. The lowercase I command actually prompts you before deleting each file. So that gives you a little bit of a safety net because it will ask, do you really want to delete this one? How about this one? How about this one? And so on. If you're deleting a couple hundred files, that can get very annoying to be prompted a few hundred times. So that's normally not the default. The -R option says to delete recursively. This is one that can be really dangerous because you're telling it delete this directory and everything under this directory. If you remember the discussion of relative and absolute paths, if you have a slash in the wrong space, or if you accidentally leave the directory you want to delete with a slash, you can delete a lot more than you intended to. Trust me, I've done it. So why did I tell you about the file command? Again, that goes back to Linux assuming that you meant to type what you typed. And when you're trying to print a non-text file like it's a text file, like I mentioned earlier, it gets interesting and makes weird noises and things like that. Sometimes you want to display the contents of a file to the screen. We talked about the cat and more commands, or I listed them earlier. Cat shows the file all at once. It will scroll by on your terminal very quickly. The more command shows you the file a screen full at a time. Now there are different versions of more out there. Some of them will let you use the arrow keys to scroll back and forth. Some of them won't. Most of them just allow you to hit the space bar to show the next screen full of data. So we have the less command, and essentially less is more. Less does the same thing that more does, but it lets you scroll using the arrow keys. So that's sometimes a little bit more friendly command to use. Again, working with files and directories, if you remember from early on, systems have the concept of both users and groups. And again, just a reminder of what those two terms mean. We've gone over it a couple of times. Users and groups are what's used to control access to files and directories. So every file is associated with a user and with a group. In more advanced systems, it may be possible to associate them with more than one group, but in general, it's one user and one group. And then every user has a home directory. I mentioned that earlier. That is your space for storing your files, and it's the directory where you're located when you complete the login process on the system. It's where you start out when you're using the system. So more operations with special files or special characters for accessing files and directories. Every single directory on the system will have two special subdirectories. One of them is dot, or a single period. Another one is two periods. Together, no space between them, just dot, dot. Dot is a kind of a circular reference to the current directory. We'll see in some later examples how that becomes useful. Although if you've been paying close attention, you've seen me using it in some previous examples today. The double dot is the current directory's parent. So the directory that's one level above where you're currently located. That can be very useful if you want to change to that directory. You don't have to type its whole name. You can just type cd space dot dot and you go to the parent directory. The tilde key We already used the backtick for some special meaning, so why don't we give the tilde special meaning as well? That's a reference to home directories, and there's a couple of ways you can use it. If you use it alone, it's a reference to your home directory. If you use it followed by some username, the example I have there is tilde John, that's a reference to the user John's home directory. So that can be a shortcut for accessing some files. Again, why do we need those? Some examples in the table. CD ... changes to your directory's parent. / some command. Remember I said if you want to run a command that's not in your path, you have to tell the system where to find it. Well, if you don't want to edit your path, / some command, that's one way to tell the system where to find it. Examples of displaying files in your home directory and someone else's directory, and also CD space tilde, which changes to your home directory. You could also do CD $home. And in another lazy programmer's note, you can just type CD and press enter. You don't actually have to specify your home directory because that's the default that CD does unless you tell it some other directory to go to. But it works for an example in the presentation here. We talked about hidden files. The way you create a hidden file or the way you identify one on the system is the file name begins with a period. And again, normal LS will not list it. You need to use the -A option to be able to see it. So other than, another note, other than that leading period to mark a hidden file and the special directories of dot and dot dot, a period really has no special meaning in file names. Personally, I work in technical support and have for quite some time on Linux-based systems. And sometimes you'll see a user, especially if they used DOS many, many years ago, where we had file names that were 8 characters and then a period and then some 3-character extension. If they want to list all of their files or remove all of their files, you might see them do ****. That's not really necessary. A dot that occurs in the middle of a file name has no special meaning. So the asterisk, the star, will match that just like it matches any other character. So that's important to remember, is that the dot inside a file name really doesn't have any special meaning. At that point, I will go ahead and wrap up everything for today, and we'll pick this back up next time when we do part 2 and go into a little bit more advanced commands and some of the interactions with the system that you might do. I will thank you for your attention. We'll talk to you on the next presentation.